So I have three different compounds here. I've got one that you're going to find out is called tetrafluoromethane. We have carbon dioxide, which you should already recognize, and then we have dichloromethane. So for each of these, we're going to discuss a little bit about their shapes, the angles, whether or not it's polar or non-polar, and things like that. So I'm going to start. It doesn't matter which one we start with, but okay. So we'll start with the first one I drew, which is the one with the fluorines. So first of all, what's the shape of this molecule overall? What's that shape? It's tetrahedral, so I'm not even going to write that out. And so what's the ideal angle here? 109.5. Yeah, that's a great radio voice there. That you have to do it. Okay, now we have to talk about whether it's polar or nonpolar. And so for this one, are there any dipole moments? Is there a difference in electronegativity between the carbon and the fluorine? Yes, so which one is more electronegative, the fluorine or the carbon? Fluorine. And so you can imagine, in physics, you draw the little ray and it looks like this, and so on and so forth. And we actually have one here. We have one here, and we have one there. So there are dipole moments that are present. Now, is this a polar or non-polar compound? It's non-polar. So just because something has a dipole moment, or has dipole moments, I should say, doesn't mean it's going to be polar overall. And so you can imagine this being like tug of war, because the fact is each of those rays are just as strong. So each fluorine is pulling just exactly the same amount or same strength from the electron density. And so overall it's non-polar. Okay. Then we have carbon dioxide. What's the shape for the molecular shape for carbon dioxide right here? It's linear. So what's the angle here? Whoops. 180 degrees. It amazes me sometimes I get people say greater than or less than 180, but you can't. For a line, it's going to be 180. That's all. Because they overthink and they think, but they're double bonds, and so no, it's 180. And it's called linear. Are there individual dipole moments in carbon dioxide? No. And so are there? Let me rephrase. Are there individual dipole moments? And is there a difference between carbon and oxygen for? Yes. Right. And so once again, which one's more? Which one? I just spit on this. Which one is more electronegative, the carbon or the oxygen? The oxygen. And so remember, when we draw our ray, or the little arrow, the plus n goes with the carbon. Same thing here. So overall, is this a polar or a nonpolar molecule? It's nonpolar. And finally, we have dichloromethane. And once again, the shape for this one would be, it is tetrahedral. I should have done one that was trigonal or trigonal bipyramidal or something, but just for space, time strain, I did that. All right. Now, are there individual dipole moments located here? Is there a difference in electronegativity between any of these atoms? Yes. What's the most electronegative of these atoms? The chlorine. And so we can once again put in, okay, one going this way. We don't usually draw them between carbon and hydrogen because they are so close in electronegativity that it's relatively negligible. So overall on this one, is this a polar or non-polar compound? This is polar. And so you can actually figure out, like you use, if you think back to physics and you talk about force vectors and stuff, the little head to tail, if you got an arrow that's going this direction and the arrow going this direction, you add them up, and if I was a mutant, then I'd be able to show a third hand that goes from this thumb to this finger. That'd be the overall pole. And so what that means is, overall, there really is a dipole moment that looks like this. There's more electron density on that half of the molecule than on the other one. So anytime that it's an uneven distribution, so even if we looked at that first one, and we just changed one of these to a Cl, it would become polar, because there is a difference. Because that chlorine is less electronegative than the other three fluorines. Okay. Let me just hit an undo though before. Oh, see, I did not mean to do that. Okay. Yeah.
What if you put the two?
So we have something like this. Maybe if I hit the little pen. So what would opposite sides look like? So you're saying here. Like this? Okay. So it's still going to have individual dipole moments. Overall, is this going to be polar or nonpolar?
Polar.
It's still polar. And why is that? What would be the assumption that's erroneous? Sometimes people say, oh, well, we got one going up and one going down, so they're going to cancel out. Because they're not exactly opposite each other. Because remember, this is in 3 dimensions. It's not 180 degrees from each other. They're 109.5. I'm just not very good at drawing it, but so please, there's going to be an arrow coming out towards us. So it's going to be a little fatter on this end, like I said, and that's supposed to be going a little away from us, but I can't draw it in. But the arrow will be coming out towards us at an angle. And so what it's supposed to say, show. Because, yeah, people, especially, a lot of times people just have the tendency to draw it this way. And then they forget. They say, oh, it's nonpolar. But they forget they drew that as square planar, and it's not square planar. You just have to always remember. A lot of times, even your book will draw it this way, rather than drawing it in 3 dimensions. But you have to remember, anytime that carbon's making 4 bonds, it's really 109.5 degrees and not 90. You know, it looks 90. Your brain's just got to start to imagine everything in 3 dimensions. And so, all right. We actually started talking about this, that curved arrow. Some books also call it arrow notation. Some of it called electron pushing. I will probably always call it electron pushing, because that's what, back in the old days, what the professor that I taught called it. Okay, the vast majority of chemistry and the functionality of it has to do with the movement of electrons. Otherwise, it's static. Right? Otherwise, it's inert. If electrons aren't moving, whether leaving or coming or whatever, it's completely inert. So we have to have a way of showing that. And this is where I talked about with respect to resonance, we use arrows. Okay, and so this always talks about, you can see the words here and blah, 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 but, and apologize that it didn't, I had to use a different program to try to make this today because the computer won't speak to the iPad. They're not getting along right now. And so, for whatever reason, it's decided to act up. Okay, so let's just do a different. So let's look at some examples. Okay. Give you a moment to draw this. I drew the structures. You need to decide if there's anything that's formally charged or not. So you make sure you draw this. One of these, by the way, is butanone, which you'll learn how to name next semester. The other one is not butanone. You hit. On the what?
On the right.
Yes, the oxygen that has a hydrogen surrounded is charged. And what is this charge on that? It's a positive charge. And remember that, I don't want to say the cheating way, because it's just not cheating, but the quick way of doing it is if an oxygen is making 3 bonds and has, here, electrons making 3 bonds, it's going to be positively charged. Okay, but everything else is neutral. And you should already realize, for example, if we look at, just to review, if we look at this carbon right here, how many hydrogens, if any, is on that carbon? 2. What about this carbon that's next to it? How many hydrogens, if any, is on that one? 0, because it's already making 4 bonds. Okay, it's making a bond here. 1, 2, 3, and then 4. So it has 0. Okay, so that's why you should hopefully start to get used to seeing it this way. Okay, so we're going to do what's called curved arrow notation or electron pushing. And there are rules of thumb. At this point in time, I wouldn't expect you to know what would be doing the attacking and what gets attacked and stuff. You will slowly but surely figure this out. Now, I would expect you that if I gave you the arrows, you could tell me what the final products would be. Or if I gave you the starting materials and I gave you the final products, you could put the arrows in. Okay. So there are rules of thumb. Even though mine always come out looking like big toes. And that rule of thumb is that the electrons, and so by that we're talking about the movement of the arrows. So and this is my abbreviation for electrons, they always move from more negative to more positive. Which makes sense. They're going to repel each other positions. So that means, whoops, I misspelled position. So for example, we would have the electron, if we had something that was negatively charged and we had something that's positively charged, where do you think the electrons are going to go? From the negative to the positive, and that arrow right there would show you that two electrons are going out and they'd be forming a new bond. It's not like, and sometimes I would have people draw in, the two electrons leave the thing that's negative and just jump on over to the thing that's positive. No, it's where here, this would be something that's negative is going to hit something that's positive, boom, and you have a new bond between them, a new single bond between them. Okay, this is just one example. Or you can have things that are delta minus going to things that are delta plus, because it's going from something that's more negative or more electronegative to things that are more positive. Okay? Or you could have a delta minus going to a positive charge or a negative going to a delta plus, or things like that. Okay, so it always goes from whatever's more electron rich to whatever's electron deficient, since we're talking about the electrons. Everything is about the electrons. So here in this example here, the way that it is, now your book doesn't do this, but I always circle it so that way it makes it a little bit easier for you to see what's moving. We have these, and it doesn't matter which of these two, but that oxygen is more electron dense, okay? And so this is one example where it's not going to hit the other oxygen. And the reason why is actually if you draw that out on your own, which I suggest that you do, isn't that lovely? They're missionaries. So once again, just a little spiel. If anyone is interested, we're having a mission small group. It's actually meeting just across the road. And just ask me about it. But we're doing that on Sunday night. But they're missionaries to Russia. They're part of the living dead. And actually, we're not allowed to say what part of Russia they're missionaries to because of the fact that their lives would be in danger. Okay. But, right, so right here, we have that oxygen, but on your own, just draw the final product as if it formed a new bond to the other oxygen. You're going to find out, weird things would happen. But this is the way that the electrons would go. The PowerPoints actually kind of break it down, and I'm trying to make it really obvious that that's a two-barbed arrow. Okay, so then let me do my final product. That is just a reaction arrow. So that's why I chose a different color here for those who aren't colorblind. To try to make it a little obvious of what's a reaction arrow versus an electron pushing arrow.
Are electron pushing arrows always colored in?
No. In fact, I can't tell. I don't think they are. I say no, and then you say, they're blue. I'm like, oh, no, it's lost on me. So you'll have to look on your book if they colored in. Yes, Bradley.
You go through my pushing electron book later.
Okay, so one of the very first things, now I'm going to draw with the final products here. Technically, we actually have two products in this example. So I wanted to pick one that's a little bit more, difficult. Okay, there's what used to be the butanone. But now the electrons that did the attacking, boom, sound effects optional, are connected to the hydrogen that it plucked off. So I used to work with a guy, and he was actually a professor too, but he also did research. He would always talk about whenever things get attacked, the thing that does the attacking is called the nucleophile. The thing that gets attacked is the electrophile. But he would always talk about a nucleophilic attack like this. He would always say, you always go after the lowest hanging fruit, the one that's easiest to pick. He goes, or that child in the street. They always seem to me a little bit sick that he talked about going after children in the street. But it does, if you're in a class and he's talking about picking kids up out of the street, then it does at least stick in your mind. I'll try to always say the lowest hanging fruit, because at least then it's more benign, not so malevolent sounding. All right. And then we actually have the second compound, which was that oxygen. It's now got 2 hydrogens. I want to point something out here. This lone pair electron there is still there on that oxygen. And I'm going to change colors just briefly, because these 2 electrons that have been holding that hydrogen on, so that's a hydronium ion. That's why I didn't want to tell you the name, because you would have figured out that it was an ion. It's called hydronium ion. But those 2 electrons that had been holding that hydrogen onto the oxygen is now a set of lone pair electrons on what is now water. And so that's why I wanted to change the colors for you that aren't colorblind. These 2 electrons here are these 2 electrons there. Okay, at the end of this, we need to also then look for formal charges. Is there anything that's charged? Okay, the oxygen, and it's the other oxygen now that's charged. Okay. And just like with resonance structure, your overall charge of what you end up with has to equal to what you began with. So that's why the way that we have it written here, we had overall was a +1, at the end it's a +1. In reality, if you're doing this in a beaker or your body's doing this in vivo, obviously it's not like a beaker full of positive charges, because otherwise it'd be the end of the world, it'd explode. But there would be a spectator anion like chloride or bromide or something like that, it'd be around. But they're just not doing anything. They're spectators, and so we don't even show them, because otherwise it may make the chemistry more confusing for people. But that's called electron pushing. Each time that shows you that there are 2 electrons moving, 2 electrons from that first oxygen go, they swipe that lowest hanging fruit, they smack that hydrogen, the 2 electrons that have been holding that hydrogen onto the hydronium oxygen now break off and they leave to make the water. So let's do another example. This time I'll let you guys figure out Okay, first thing you want to do is look to see if there is anything charged that I did not write in. And then I'll give you a moment and I want you to write the final product or products here. So one of the big differences is that the chapter order is different. Free radicals used to be included in the alkane, alcohol chapters, and now it's got its own towards the end of the semester. And the order of the chapters are also different, but that's why usually I cover this within the second week of class. Okay, just review from Gen Chem, because it may have been a while. These are reaction conditions. Does anyone know, what does the delta sign mean for a reaction condition? It's heat. That's actually one way that they show heat. Okay, because yes, it's a change, but they're talking about the change in temperature. They're adding heat. Does anyone know what H nu is? That's not a V, that's the Greek letter nu. H nu. That's light. Because remember from physics and from Gen Chem, E is equal to h nu, that's the amount of energy in a photon of light. And so the way that they show light being conditioned is they put h nu down. Okay, and so the reason why is this, we're going to see free radical, this is free radical halogenation. And this does naturally occur, this occurs up in the atmosphere, the whole destruction of the ozone layer, because you get free radicals to form, and because of the heat and the light and all that kind of stuff. But all right, so when we talk about the barbs here, for example, and I really exaggerate it, that's a single barb arrow. And that's a single barb arrow. So before the chlorine, remember chlorine, fluorine, hydrogen, bromine, iodine, those are naturally, nitrogen for that matter, those are naturally occurring diatomic elements. Like you do not find chlorine just by itself. It's always with another chlorine gas. For chlorine gas is Cl2. Okay, but you add heat and light, they break apart, and what we're going to get, and I'm going to try to keep this color coordinated, we're going to have the chlorine that was on the right will look like this. Oh, wait a minute, that's a different color. And then we're going to have the chlorine that was on the left, so to speak, look like this. Because only one electron was moving each time, so that's why it's a single barbed arrow. You don't see them very often, okay, but they do exist. And there are times it's very important. Some of the more complex electron pushing mechanisms have intermediate steps that utilize free radical movement, okay, so, or even electron rearrangements. But I just want you to see what examples of that look like. All right, this is just to show examples of what we've been doing. They're showing you that, I think those are color coordinated. I don't know if they're always color coordinated in your book or not, but this is just showing you that, for example, we have the hydroxide anion coming, smacking that carbon, popping off the bromine. We end up with a bromide anion and methanol. And so they're just showing you the different examples that you could, remember, it's always going from things that are more negative or more electron rich and smacking things that are more positive. Here it's something that's delta plus, okay, or electron deficient. Once again, this is more negative. This one's going to be more positive. Okay, and so on and so forth. Okay, for the rest of the time, we're going to really be talking about acids and bases. And when we do acids and bases, there are, well, in theory, there are three definitions. There's the Arrhenius one, which is the original one, which an acid was H plus and a base was OH minus. But that's outdated. And then there's Brønsted-Lowry, okay? And so Brønsted-Lowry is this one, where an acid is something that gives off an H plus. It's a hydrogen donor, and the base was a hydrogen acceptor. And then the third kind is called a Lewis acid, Lewis base, which all has to do, instead of looking at the protons, it looks at the electrons. Okay, so those are the three kinds. You really only need to know Brønsted-Lowry and Lewis acid, Lewis base. And so once again, just to give a broad generalization, this one's looking at it with respect to the proton, whereas I like to think about the Lewis acid base. They are related, but instead of looking at it from the aspect of the proton, it's looking at it from the aspect of the electrons. Okay, so the first one, the Brønsted-Lowry, they have an example of that right above. It's things that you've seen before. It's just that in Gen Chem, you didn't draw arrows in most likely. But it should make sense here. We've got the base. The base is either going to be negatively charged. It's got to have, by definition, by the way, that's a rule of thumb. I'm just not going to draw it in there. But a rule of thumb that all nucleophiles must have lone pair electrons. You cannot have a nucleophile that doesn't have lone pair electrons. And so, all Right. In fact, the abbreviation for nucleophile is NU with lone pair electrons. So this is the abbreviation for later on. Whoops. That's nucleophile. So here we have a nucleophile, the base. It comes, it smacks that hydrogen. Boom. Sound effects optional. And then this bond breaks. And so we get the conjugate acid and the conjugate base. The base always becomes a conjugate acid. The acid becomes a conjugate base. If it's a weak acid, weak base, it's reversible. If it's a strong acid, strong base, it's irreversible. So that's nothing new, completely. Just a review from Gen Chem 2. And that's Brønsted-Lowry in a nutshell. Okay, so this is just the words for it. A Brønsted-Lowry acid donates the proton. The base accepts the proton. And that's as far as we're going to take that for right now. And they're just showing the curved arrows, so we're going to spending more time. Okay, unfortunately, this did not separate out. So I'm just going to show you what. I'll just write it down here real quick. You have to. This is just equilibrium constant, and so they look at the acid dissociation for the equilibrium constant. You could do the same thing for the base, but we never discuss KBs, hardly ever. In biochemistry and organic chemistry, and even in biology, they always do things from the point of view of the acid. So you only hear them talk about pKa's and Ka's. And if you think back to Gen Chem, Ka times Kb has to equal K of water, which is 1 times 10 to the minus 4. And that's why if it's neutral at pH 7. But once again, that on your own, you should probably review that because I'm not going to go into any greater detail here with respect to it. All right. Now, that being said, and I wish they wouldn't have done this, Ka's, or equilibrium constants in general, tend to be either huge or very, very small, like negative, like 0.000001 or 1 times 10 to the 6. And so those are just ridiculous for us to use and to think about, really think about in your head. It's kind of hard to keep all the zeros and everything in mind. And so we use a mathematical formula that there's a function. I'm sure it probably has a nicer name ultimately for it, but I don't know. I just call it the P function. And so P is equal to negative log base 10 of whatever. So that's why pKa is negative log base 10 of Ka. pH, which is what you're probably used to, is negative log the concentration of H. You could have P students, and that'd be negative log the number of students that we have, in this room. It's whatever. P is just a mathematical function, but it makes those numbers much more manageable. So then pH 7 is when the concentration is equal to 1 times 10 to the minus 7. That would be a pain to always say that, but by saying pH 7 makes it all more easily. So you have to realize it's an inverse log because it's a negative log. So a low pKa means it's a stronger acid. A high pKa, the bigger the number, the weaker the acid. The stronger the acid, the lower the number. Okay, and so that's what this is just trying to show here. We have methane, we have, hydroiodic acid, which kind of gives it away. And so methane, we're talking about the pKa is 60, but you have to realize that means it's not acidic at all. And HI, which has a pKa of, it's 10, it's negative 10. That's supposed to say 10 to the minus 10, but it's not 1010. It's 10 to the minus, it's 10 to the 10. Sorry. That's why it's negative 10 overall. Okay, because it doesn't, unfortunately, just like the PCs and the Mac don't talk, this program doesn't like superscripts. Okay, let me see if I can get this to... Here we go. So this is just examples. We have our strong acids. Remember, there are only a handful of strong acids. Hydrochloric acid through down to hydroiodic acid to be strong. HF is not. Hydrofluoric acid is not a strong acid. You like nitric acid, sulfuric acid, and phosphoric acid. Oh, well, we'll get back to phosphoric. Nitric acid and sulfuric acid are strong. Selenic, if you had selenic acid, would be strong. But then there's a whole bunch of weak acids. And so they're just trying to show you this table. And we're going to talk about, like, you can look at the acid, or on your own, look at the acid and figure out what the conjugate base is and so on and so forth. But what I want you to really think about are the structural functions or factors that what makes an acid a strong acid or a weaker acid. And you should start to be able to compare two different acids and be able to say this one's going to be stronger or this one's going to be weaker. Okay, so there are 4 things that affect the acidity of that proton. When we say acidity of the proton, that's the ability for the hydrogen to leave. 1 is the strength of the bond between H and the A, whatever A may be. So that's 1. 2 is the electronegativity of the parent atom, whatever A is. 3 is the electronegativity of the atoms nearby. And 4 is, it's probably the most difficult one to discuss or for people to imagine, is you have to look at the conjugate base, what the product is, and look to see if it's stabilized due to resonance. Okay. So these are the 4. The strength of the bond between the hydrogen and the parent atom, and we're going to go over examples of that in just a moment. We're going to talk about the electronegativity of the atom from which it's attached to. Then we'll talk about the electronegativity of the other atoms in the area, and then finally, resonance of the conjugate base. Let me see if it didn't. So I made a copy where that was blacked out, or where it was a box and stuff. I could discuss it a little bit more. All right, so let's compare. We have HF, and we're just going to look. You could look HF, HCl, HBr, HI. I'm only going to draw HF and HI because we're looking at trends here. Think back to Gen Chem. Which one of these, fluorine or iodine, is larger in size? Iodine. So I'm going to, this is not drawn to scale. Your book does a bit. We have this little hydrogen, and we got a big old iodine. And there's the one electron that they're being shared is where they two intersect. Then we have fluorine, so we have little hydrogen, and we have little fluorine. Okay, and I can't even, made it so small that you can't even really draw in there that one's fluorine and one's hydrogen. Now, so first of all, when you're looking at a column on the periodic table, sorry guys, but size matters. Contrary to what you may believe, size matters here at least. And that's, so which is going to be the stronger acid, HF or HI? So you have to think about what it means for something to be an acid. What it means to be what does an acid do? Donates a proton, which is an H+. What happens to the electron when it donates that proton? It stays behind. Okay? So which one of these do you think is easier for the hydrogen just to kind of leave? The bigger, the sizer one. The bigger sized one. All right. And the reason why is that if you remember, the nucleus, I should say, of that iodine is still really tiny. It's the electron cloud that's huge. So the parent nucleus here, which I'm going to attempt a bit for the fluorine, is still relatively close to the other hydrogen. So it's sort of like those parents that keep their children on a shorter leash. Whereas you have this iodine here with its little nucleus, and you have this hydrogen over there. It's so much easier for that hydrogen to run off, but it just leaves its electron behind. So whenever you're looking at the same column on the periodic table, it's the size of the parent atom. Okay, that's scenario number 1. Okay, it becomes more acidic. That's why HI is much more acidic than HBr, which is much more acidic than HCl, and which is much, much more acidic than HF. HF actually is not even considered to be a strong acid at all. But you can look at the same thing. We could compare H2O versus H2SE. Water versus hydrogen selenide. Which one of those is going to be the stronger acid, water or the H2SC? H2O or H2SC? Which one's going to be stronger? H2SC. Okay, so this is a stronger acid, and for the same reason. Okay. So it's if you're looking at it with respect to the same column, but what if we're looking at it with respect to the same row? So now the easiest one for me to do and to rationalize is if we look at that second row. So we have HF, and we just go next door is H2O. Next door to that is ammonia, NH3, CH4, so on and so forth. Here, though, it's not size. It's electronegativity. Because now, if you think about it, I'm not even going to attempt to draw these in, but remember, electronegativity is how easily that parent atom wants to draw electrons and keep the electrons to it. So to me, I always thought this was the easiest one of all four scenarios to keep. Which of these, which on the extreme is the strongest acid? Is it going to be methane, CH4? Is it going to be HF? HF, I mean, the name is hydrofluoric acid. So it kind of uses why it's always easy for me to remember. The fluorine is so electronegative, it likes to keep that electron, and it could care less about that hydrogen. I shouldn't say care less, but because I'm anthropomorphizing it. But whereas the carbon and hydrogen are roughly about the same in electronegativity, and so that hydrogen doesn't actually leave. In fact, it's what pK was like 60 versus HF, which is, I don't have it memorized, but it's much lower, but it's much lower than methane. So that's why if we were looking at the trends here, this is the stronger acid, followed by water, followed by ammonia. Ammonia you should memorize from Gen Chem. Ammonia is a base, and methane is inert. Not a nerd, but inert. Okay. So that's scenario number 2. Scenario number 3 is actually along that same line. So I'm going to draw this. This is ethanol. And then this looks an awful lot like ethanol, but there are 3 fluorines right here. First of all, I picked something that's relatively simple to figure out which hydrogen is the hydrogen that would be moving. Which hydrogen is going to be popping on or off? The one on the oxygen. Because first of all, it's almost impossible to remove a hydrogen off of a carbon. Remember, they're about the same electronegativity. Whereas there is a difference between that and the oxygen and the hydrogen. So now, ethanol, which is that top one, that's ethanol. This one, by the way, if you had to name it, would be 2,2,2-trifluoroethanol, which you'll learn how to name later on. But it's a trifluorinated ethanol. Which one do you suppose is going to be the stronger acid? The one with fluorine or the one without? The one with fluorine, and it's called the inductive effect. So there's your good Jeopardy word. Okay, inductive. Because it induces it to be more acidic. And the reason why is the fluorines themselves are so electronegative that it actually pulls more of the electron density this way. By pulling the electron density, it makes that proton easier for it to leave it behind. Okay? And one of these slides, it actually has numbers associated with it. I would never expect you to memorize the numbers, but to understand the logic. So I've covered the first 3. And in reality, I think that's almost all of chapter 1. It's just the 4th one I will try to touch on briefly in the next class. But that then we're going to actually focus primarily on chapter 2 and move on to chapter 2.